Welcome back, Falcons. We are in our last throes of Unit 2. So this video, we should hopefully cover the rest of converting curvilinear functions, go over a couple examples, and then wrap up this unit. Now, if you do notice, there are extra problems and answers at the end of these notes. So take advantage of that, especially if you need any help walking through the homework. Okay, so this is from your textbook. As we talked about, AP loves logs. So let's just go as to why that is the case. Now, if you think back to your math classes, whatever you've taken before, if we have an exponential function, this model is the zero power in the ladder approach. And it's useful for values that grow by percentage increases, which is why we're taking the log of the y value. If you have a logarithmic function, it's generally graphing exponents. So a wide range of x values, or the scatter descending rapidly at the left but leveling off towards the right, may benefit from trying out a log model. Versus the power model, which is like the Goldilocks model, when one of the latter powers is too big and the next is too small, we might want to try taking the log of both sides. Now, this might seem like an inexact science, and it really is, because there's no perfect way of fixing curvilinear functions. This is the art towards statistics, where we're just trying to go through each part and see what works. So if you go to your calculators, whether it's on the TI Nspire or the TI-84, it is possible to fit an exponential or power model to your data using the calculator. They have an exponential regression model, they have a power model, and they also have a logarithm model. You can see if you go stat calc, exponential regression or power regression, or log regression. Again, they use natural log, which is ln, or log base e, with e being Euler's number at 2.71. Remember, an exponential function is a linear regression on x with the log of y. A power function is a linear regression with ln of x with ln of y, and the log function is the reverse. So it's a linear regression of log x with just the y values out, what we saw in the previous slide. For a visual examination for re-expressing the data, remember, our exponential function opens up. With our power function, we could be one half or the other half of, let's say, an x squared function, and a log is like this. You want to apply the re-expression that is the inverse of the shape of your data to attempt to straighten the distribution. The bottom line is to try re-expressing the data to get the best fit. You may need to try several options to find the best fit. Remember, as always, it ain't ever going to be perfect, because we know our models aren't. We're looking for best, not perfect. So this statistician who came up with this ladder of powers, his name's Tukey, if you want to look it up, came up with this figure off and to the right, and we're going to utilize this to examine our curves. It actually is kind of helpful. This figure is designed to suggest where on the ladder we would go to find an appropriate transformation. The four curves labeled 1, 2, 3, and 4 represent shapes of curved scatterplots that are commonly encountered. So let's say your data looks like this. Well, if we want to linearize it, we could either go up the ladder on the x or go up the ladder on the y. So let's say if we're at 1, we could either square the x or square the y. If we were in quadrant 4 with this type of bend, it's saying we can either go down the ladder on the x values, so maybe take a log or the reciprocal function, or we could go up in power on the y. So that's how I want you to be able to read this graphical display. Usually we're going to try to fit this onto our curvilinear functions to see what direction we should go on our ladder of powers. So just as a practical example, if our curve looks like this and we have our ladder next to us, if our curve looks like number 1, we either want to go square the x or square the y, which is what we said before. If our curve looks like a number 2, where it's kind of the right side of a quadratic, or maybe it's exponential growth, maybe you want to try to square the x's, keep the y's the same, Or maybe we want to square root the y's. Or we could go down further if we need to, and maybe we can take the log of the expression. So if the curvature in the original scatterplot looks like curve segment 2, I'll power down the ladder for no transformation for y, and or power up the ladder, x squared might be used. So let's try one of these. I'm going to jump over to my TI Nspire, and then we're going to look at this example. So whitewater rafters know that a river flows more slowly close to its banks due to depth and friction. To study the nature of the relationship between water velocity and the distance from the bank, data was gathered on velocity in centimeters per second of a river at different distances in meters from the shore. So the goal is to enter and graph this data and then describe the scatter plot. Whenever we see describe the scatter plot, I want you to think shape, outliers, direction, and spread. So jumping over to our calculator, just because I want to save some time for you guys, I have my distance and all of the values entered along with the velocity. If we switch over to the scatter plot, we can see that this is a positive, moderately strong, potentially linear function. So in order to tell if a line would be a good fit, we should remember not just looking at the scatter plot, but we should look also at the residuals. So if I go first regression, show a linear model, there's our linear model. Then I have to go menu, analyze, residuals, show residual plot. Here is where we see a big difference. In our residual plot, we definitely see a curve. So as I slide through the notes, you can see that on slide 29, we have our line of best fit, which is 22.8081 plus 0.7372. If we did our analysis on the spreadsheet, we would go statistics, stat calculations, linear regression. Again, we want our distance as our y and our velocity as our x. We're going to hit OK. We see we have our y-intercept, we have our slope, we have our r squared of 86% of the variability in the velocity is due to the distance, and our r, which is a pretty strong correlation. It should be a pretty good model, but as we looked at the residual plot, it definitely is curved. And that's not as good as we thought it was. So we should be able to do better. Now, if we look at our scatter plot and we fit the curve, looking at our notes, if we fit which curve we could look at on the Tukey's ladder of power, we see that our data looks more like segment 4. So what we can do is we can either go up the ladder and square the y's, or we can go down the ladder and square root the x's. So we're going to go to the 1/2 power. So what we are going to do, and this is new, is I'm going to go back over here. I'm going to say root data. And what I'm going to be able to do is under this equals line, I can start typing in a formula. So what I'm going to say is control x squared, and then I'm going to type in my variable. Since I already have distance, it's going to take everything that was in column A and take the square root of those values. So this is going down the ladder on the x's. And now if I switch over to my graph, all I want to do is switch from distance to root distance. And now I can see the linearization of my plot in real time. My velocity stays the same, and the residuals look slightly more scattered. So this is a better model. Now I can look at this data. If I just put the residuals on the x-axis, and I go menu, plot type, I can look at a histogram or a normal probability plot. Now, if you think back, a normal probability plot we should mostly fit on a line if my data is linear. So as we went through this problem, we looked at the basic graph. We saw that a line wasn't a very good fit because the residuals was definitely curved. We took the square root of the distance values and saw that it was a much better example. We're going to do one more problem, and this involves Moore's law. So with Moore's law, Gordon Moore of Intel, like the processors, predicted in 1965, so a long time ago, that the number of transistors on an integrated circuit chip would double every 18 months, which is called Moore's law. At the right are the data on the dates and number of transistors on the Intel chips. The goal is to make a scatter plot of the data, use years from 1970 as the predictor variable. Okay. Again, I went ahead and typed in this data. As you can see, we have our years from 1971 all the way up to 2010. And then the number of transistors, as we type those in, increases at what appears an exponential rate. What we want to do is come up with a scatter plot. So if I switch over and I do a scatter plot, already have it available, or if we go over to the slides and see, this is definitely not linear. All the numbers were relatively small, and then from about 2000 on, the growth was exponential increase. This ain't good. So it's obviously an exponential function. So that's y equals a times b to the x. So to linearize an exponential function, we're going to try logarithms. Now, just as a brief aside, I want you to think back to when you learned logs before. We should know that when you have multiplication inside a log, it separates out to addition. Likewise, when you have division inside a log, it turns into subtraction. If you have exponents, exponents move out front. So now look at what we have. We have y equals b to the x. So if we took the log of both sides, we would have log base b of y equals x. If we had y equals a times b to the x, which is that exponential function, if I took the log of both sides, I would have the log of y is equal to a times b to the x. Well, that's multiplication, which separates out into addition. We said exponents go in front, and so we're left with log of y equals log a plus x log b. Interesting. If I just tell you that log a and log b are just numbers, that looks linear, doesn't it? And that's the goal. When we're taking the logarithmic expression, or the log of both sides, what this does is, in fact, turns this equation into a linear function. So suppose you have a data set that looks similar to the graph. It looks similar to the function y equals log of x, or it could be the square root of function. Like, if we know what this basic shape looks like, then we might try to make our predictor, our model, be a plus log x, or we could say y hat squared is equal to a plus bx, or we could say log y hat is equal to a plus b log x. These are our three type of options when we see a curve function like this. What happens if our curve goes downward or concave down? Maybe it looks like our graph 1 over x that we should remember. So what we could try is, again, we could say a plus b log x, or we could take the log of the other side, log y hat is equal to a plus bx, or we could do the reciprocal function, which is the same thing as y to the negative first power, or 1 over y hat is equal to a plus bx. These are the options that we have to play around with. If our graph looks like an exponential function, it should start sounding familiar. Or it could look like a quadratic. Well, a quadratic would mean we either square root y hat, or we take the log of y hat, or we take the log of both. Again, all of these are just suggestions as to how to handle these types of scatter plots. Okay, back to Moore's law problem. Let's take the log of the value that is growing so fast, so the number of transistors to be more specific, and we're going to use the ln function, so log base e, as opposed to log base 10. If I go over back to my spreadsheet, I'm going to say ln log trans. I'm going to say equals ln. So I can just type in ln, or I can use the ln function, which is in the blue part for e, parentheses, and I just type in my variable, transistors. And since it bolds it, because it knows what it is, and I hit enter, now I get the log of each of those values. When I go over to my scatter plot, instead of having transistors, I'm going to graph log trans, and I'm going to run my linear regression model. And by doing that, I can definitely see that looks like a line. To verify, I'm going to pull up the residual plot. Remember, when I look at the residual plot, I do not want to see a pattern. Now, at the end, it looks a little different. If I do a linear regression model, so statistics, stat calculations, linear regression, my x is going to be years. My y is going to be log transistors. I should get something that looks like our y-intercept is 7.0647. Our slope is 0.365835 with a standard error of 0.5444 and an r squared of 98.9. Everything else we can forget, just so you recall. So using our model, we have our y-intercept and our slope. It's asking us, can we predict the number of transistors in 1990? Since that's part of our data set, we are going to then plug in 1990. Now, I want you to think about, how do we actually use this? Remember, our new linear model is predicting ln of y. So if I plugged in 0.36583 parentheses 1990, that's not what y is equal to. That's what ln of y is equal to. Or when I type this all in and I get ln y is equal to 14.381, realistically, y is equal to the exponential to raise to that power. So what I do is I take e of both sides. This number is much more reasonable than what it allegedly predicted, which was 14.381 transistors. We know it has to be much larger. If I wanted to predict the number of transistors in 2020, what I'm going to do is plug in years since 1970. If I go to my calculator, and this is always years after, I can go 7.0647 plus 0.36583 parentheses. 2020 would be 50 years after 1970. So if I type in 50 and I hit enter, I get 25.3562. Well, what I want is actually e raised to that answer. So if I hit enter, now I get 1.02815 times 10 to the 11th power. If it was times 10 to the 12th, that's a trillion. So a little under a billion transistors are going into your phones right now, which seems crazy, but it's true. So the last bit is just a quick summary. Summary of re-expression. What do we have? We have logarithmic model. We have our exponential model, our power model, which is where we take the log of both of them. We have our square root model, which is either squaring the response variable, or a quadratic model where we're square rooting the y variable, or the reciprocal model. Each of these is useful for curvilinear features, and I want you to think, Where are you along this circle? A little example, a little astronomy. The table shows the length of a year for a planet based on the distance from the sun. It might be curved if we are trying to line a best fit. Once we look at the residuals, it's definitely curved. So once we see that there is a curve in our residual plot, there is work for us to do. Now, what do? Well, we first try taking the log of just the distance. If we take the log of the x values, does that straighten it out? We get an r and an r squared. That's not all that much better. Maybe we take the ln of years instead of the ln of distance, and we get still better, but it could be better. If we take the log of both, or the ln of both sides, then we get an r of 0.99999, r squared of 0.99999. That definitely worked. So sometimes you're going to have to apply multiple operations to your model, and it's an inexact science. What we want to do is we want to check our plots and then verify our models with the residuals. We are always looking at a linear model. So you can verify the residuals that there's no plot here, or you can look at the histogram of the residuals, which we did in chapter 8, and we want it to be unimodal and roughly symmetric. And if we get that, then we can justify a linear model. So we have a good model, and it predicts the length of year for a planet 313 million miles from El Sol, the sun. So if I wanted to plug in the distance, I'm plugging in 313. I'm getting a number, and then I'm taking the exponential of that to get the equivalent Earth years. So we could say, using this model, a planet 313 million miles from the sun is predicted to have a planetary year equal to about 6.1675 Earth years. Now you might be asking yourself, Mr. Swenson, this is a lot of calculation. Am I ever going to be asked that? No. Most of the time, the AP is going to give you the appropriate operation, generally a log, and it's going to ask you to then use that model to do these calculations. Now, other of you are going to say, well, it's on our calculator. Why not just use a curve? If there's a curve in a scatter plot, why not just fit the curve to the data, you might be asking? And most of the time, that is exactly what statisticians do. Unfortunately, the mathematics and calculations for curves of best fit are considerably more difficult than lines of best fit. We are typically preparing results for consumption by people who may not be as sophisticated in these types of math concepts. Besides, mostly, straight lines are easy to understand. We know how to think about slope and y-intercept. It's been ingrained in you since like 7th grade. The majority of people understand lines. So we go with lines as opposed to these curvilinear functions. Caution, caution, caution. Do not expect your model to be perfect. It's not going to be there. Don't stray too far from the ladder. Some ladders include cubing and cube root, but going beyond that may lose your audience. So just always be careful. And finally, don't choose your model based on R squared alone. R squared is a good indicator of reliability of the model, but only if the model is linear. Make certain the model is appropriately linear. We have ways of checking. Beware of multiple modes. When we have multiple modes, high points and low points, this is a point where we cannot just find a x cubed function or an oscillating function that fits this. We might be better off, like we did before, of strictly looking at portions of this model to linearize. Re-expression can straighten many bent relationships, but not those that go up, then down, or down, then up. So rather than simply throwing in the towel, consider multiple models. That is the strategy. And lastly, be on the lookout for, watch out for negative data values. It's impossible to re-express negative values by any power that is not a whole number on the ladder. Imaginary numbers do not have any use in statistics. And then also watch out for data far from 1. Data distributions all very far from 1 on the ladder require a large range for re-expression. If all the data values are large, I think years or incomes, consider subtracting a constant to bring the data values near 1. So that takes us to the end of chapter 10. That is also the end of unit 2. As we start reviewing, make sure that all of these concepts that we've identified from chapter 7 on shape, outliers, direction, and strength, to least square regression lines, to regression wisdom, to how do we fix curvilinear functions, that we understand the basic properties of identifying what slope is and how do we describe it, identifying the y-intercept, and understanding what r, r squared, and s sub e are. So with that, I will see you all in the next one, Falcons.